During World War II, over 13,000 Warhawk planes proved their worth in combat zones across the globe, from the scorching deserts of North Africa to the humid jungles of the Pacific. The Curtiss P-40 Warhawk represented a remarkable achievement in aircraft engineering, combining robust construction with innovative design solutions that helped shape modern military aviation. The P-40 Warhawk fighter plane's exceptional durability and advanced engineering features stood out. The Curtiss Warhawk demonstrated numerous technical breakthroughs, from its precisely calculated weight distribution to its innovative cooling system. The P-40 Warhawk's design incorporated sophisticated solutions for combat survivability, maintenance accessibility, and weapons integration, making it one of the most significant fighter aircraft of its era. So what makes the P-40 Warhawk so superior? Let's find out in this video. Revolutionary design features. Initially designed as a modification of the P-36 Hawk, the Curtiss P-40 Warhawk incorporated several groundbreaking engineering features that set new standards in fighter aircraft design. The P-40 Warhawk's most notable structural innovation was its robust 5-spar wing design, which enabled the aircraft to withstand high G-turns and survive mid-air collisions. Subsequently, the semi-modular construction approach made the Warhawk particularly suitable for field maintenance, allowing quick repairs and parts replacement. The P-40 Warhawk stood out for its remarkable aerodynamic performance, particularly at medium and high speeds, where it excelled in maneuverability and stability. Notably, it achieved one of the fastest maximum dive speeds among early World War II fighter aircraft, showcasing its ability to excel in combat scenarios requiring high-speed descents. The aircraft's impressive design was the result of extensive wind tunnel testing conducted at the National Advisory Committee for Aeronautics Facilities. This rigorous testing process allowed engineers to refine and optimize several critical features. One such enhancement was the relocation of the glycol coolant radiator to a chin-mounted position, a modification that not only improved cooling efficiency but also contributed to the plane's streamlined profile. Another key advancement was the redesign of the air scoop, which was reconfigured to incorporate the oil cooler intake, resulting in reduced drag and improved overall performance. Additionally, adjustments to the landing gear doors and exhaust manifold configuration further the aircraft's underscoring the P-40's engineering sophistication and adaptability. The engineering team focused on achieving optimal weight distribution through precise calculations of the longitudinal center of gravity. This careful balanced consideration affected combat maneuverability at various speeds, overall flight stability across different altitudes, and performance in diverse combat scenarios. A notable manufacturing innovation included a specialized truck rig system at the Buffalo plant, which transported the Warhawk's main components, the wing and fuselage, separately for final assembly. This approach additionally helped maintain precise weight distribution during the production process. The P-40's tight turning capabilities at medium and high speeds were a direct result of its weight distribution engineering. Specifically, the aircraft demonstrated remarkable agility at lower altitudes, where its structural strength and weight distribution allowed for aggressive combat maneuvers. The engineering team achieved this balance through careful component placement and structural reinforcement. Additionally, the design allowed for modifications to accommodate different engine types without compromising the aircraft's fundamental balance, as evidenced by successful adaptations for both Allison and Packard Merlin power plants. Engineering the power plant. The heart of the Curtiss P-40 Warhawk's performance lay in its power plant engineering, which centered around the Allison V1710 engine. This liquid-cooled V12 power plant was selected for its sturdy construction and predictable power curve. The integration of the Allison V1710 engine presented unique engineering hurdles. The engine produced 1,040 HP at sea level, rather modest compared to contemporary fighters. Moreover, the single-stage, single-speed supercharger limited the aircraft's high-altitude performance. The engineering team faced the challenge of optimizing the engine's placement while maintaining the aircraft's aerodynamic profile. The P-40's cooling system represented a pivotal advancement in aviation engineering. It addressed the challenges of maintaining engine performance under demanding conditions. Following thorough wind tunnel testing, engineers devised a series of innovative solutions to enhance the system's efficiency and reliability. One of the most significant improvements was the relocation of the glycol coolant radiator to a forward chin-mounted position. This strategic repositioning not only optimized airflow but also contributed to the aircraft's overall streamlined design. Another key innovation was the integration of the oil cooler air intake directly into the radiator scoop, reducing drag and simplifying the cooling assembly. Additionally, the exhaust manifold configuration was refined to improve heat dissipation and airflow dynamics. These enhancements collectively enabled the P-40 to maintain consistent engine temperatures under various operating conditions, ensuring reliability during extended missions. The cooling system's exceptional efficiency proved particularly advantageous in diverse and extreme climates, from the frigid altitudes of high-altitude combat to the intense heat of desert operations, further solidifying the P-40's reputation as a versatile and robust fighter aircraft. The engineering team achieved remarkable success in optimizing the P-40's power-to-weight ratio through a series of innovative advancements. These efforts not only enhanced the aircraft's performance, but also made it more cost-effective to produce, reflecting a balance between technological sophistication and practical efficiency. One breakthrough came from the redesign of the engine mount system for the Allison V1710 C-15 engine. The improved mount reduced weight while maintaining structural integrity, allowing the aircraft to handle the powerful engine's output more effectively. In addition, engineers focused on enhancing the reliability of the engine's mechanical supercharger, a critical component for maintaining performance at higher altitudes. These reliability improvements ensured that the supercharger could deliver consistent power while reducing the risk of mechanical failure during combat operations. Equally significant was the development of specialized manufacturing techniques aimed at streamlining production. These innovations dramatically reduced the cost of producing the Allison V1710 engine, bringing it down from $25,000 to just $8,500 per unit. This cost reduction not only increased the P-40's affordability for mass production, but also ensured that high-performance engines could be manufactured at scale, supporting the Allied war effort with a steady supply of capable fighter aircraft. The continuous refinement of the V1710 engine accordingly led to significant improvements in operational capability. The engine's service life increased from 300 hours to 1,000 hours for less stressed power plants. The modular design approach facilitated easier maintenance and allowed for rapid field repairs, while the standardization of parts enhanced reliability across all variants. The engineering team's efforts resulted in an engine that, although facing limitations at high altitudes, proved exceptionally reliable in combat conditions. The V1710's durability was evident in its ability to withstand significant combat damage and continue operating effectively. This robust performance, coupled with the innovative cooling system, established the P-40 Warhawk as a dependable fighter aircraft, especially in low to medium altitude operations. Combat survivability engineering. Combat survivability stood as a cornerstone of the Curtiss P-40 Warhawk's design philosophy, setting new standards in fighter aircraft protection systems. The engineering team prioritized pilot safety and aircraft durability through innovative protective features. The P-40's armor protection underwent substantial advancements throughout its development, reflecting the increasing demands of air combat during the early stages of World War II. A significant milestone in this evolution was achieved with the P-40 Billion variant, which introduced a more comprehensive and sophisticated approach to pilot and aircraft protection. The engineers prioritized pilot safety by incorporating heavy-duty armor plating position behind the cockpit. This protective barrier, weighing approximately 100 pounds, was meticulously designed to shield the pilot from enemy fire while maintaining a balanced impact on the aircraft's performance. In addition to this, the introduction of a bulletproof windscreen assembly provided further security. Constructed with non-shatterable glass, the windscreen ensured both visibility and protection, even under direct attack. Recognizing the vulnerability of critical components, the engineering team also focused on safeguarding the engine. specialized armor shielding was added to the engine compartment, reducing the risk of catastrophic damage from enemy projectiles. Furthermore, an innovative adjustable armor plating system was developed, allowing vertical positioning adjustments to provide adaptable coverage based on mission requirements or pilot preferences. These advancements collectively elevated the P-40's survivability, transforming it into a robust and resilient fighter capable of withstanding the rigors of combat. The integration of cutting-edge armor solutions demonstrated the engineering team's commitment to protecting both the aircraft and its pilot, the P-40's effectiveness across a range of challenging operational environments. The Warhawk's structural integrity emerged as one of its defining characteristics. The aircraft's robust construction enabled it to withstand forces exceeding 9 Gs. Notably, the P-40's 5-spar wing design proved instrumental in surviving high-stress maneuvers, and, in some cases, even mid-collisions. The structural reinforcement yielded remarkable results in combat scenarios. The Warhawk demonstrated superior durability compared to contemporary fighters like the Japanese Zero, primarily due to its reinforced airframe. The P-40's structural strength allowed it to maintain combat effectiveness, even after sustaining significant battle damage. The development of the self-sealing fuel system for the P-40 marked a groundbreaking advancement in aviation safety and survivability, addressing one of the most critical vulnerabilities in combat aircraft. These specially designed fuel tanks were engineered to significantly reduce the risk of catastrophic fires or fuel loss caused by enemy fire, ensuring the aircraft's operational integrity and improving pilot survivability. Central to the innovation was the tank's layered construction, which combined materials selected for their complementary properties. The outer layer was made of vulcanized rubber, a tough and durable material capable of withstanding the initial impact of projectiles and environmental wear. Beneath this was a middle layer of reinforcing fabric, providing structural stability and additional resistance to tearing or puncturing. The innermost layer, composed of untreated natural rubber, was the cornerstone of the self-sealing mechanism. The system's protective capabilities were activated immediately upon bullet penetration. When the untreated natural rubber came into contact with the leaking fuel, it reacted by expanding and filling the puncture. This rapid response effectively sealed the breach, preventing further leakage and mitigating the risk of ignition. The self-sealing action allowed the aircraft to maintain functionality even after sustaining damage in combat. The self-sealing system proved particularly effective against both .50 caliber bullets and occasionally even 20mm cannon shells. This technology significantly enhanced the P-40's combat survivability, as evidenced by its superior performance against aircraft lacking such protection, including the Mitsubishi A6M0. The combination of these protective features resulted in an aircraft that could withstand considerable punishment while maintaining operational capability. The P-40's robust construction enabled it to operate effectively from rough frontline airstrips, demonstrating exceptional serviceability rates. Nonetheless, these protective features did add considerable weight, which affected the aircraft's overall performance characteristics. Manufacturing breakthroughs. The Curtiss Aircraft Company's manufacturing prowess reached new heights with the P-40 Warhawk program, marking a vital moment in aviation manufacturing history. In May 1939, the company received its largest ever fighter production order of 524 units, valued at nearly $13 million. The manufacturing process benefited from several groundbreaking innovations. A notable advancement was the implementation of a specialized truck rig system at the Buffalo plant, which transported the Warhawk's main components, wings and fuselage, separately for final assembly. This innovative approach enables streamlined component shipping, making final assembly efficient while minimizing production bottlenecks and improving quality control. The manufacturing success of the P-40 Warhawk resulted in remarkable production figures, with 13,738 units built between 1939 and 1944. Hence, the Warhawk became the third most produced American fighter of World War II. The quality control system developed for the production of the P-40 Warhawk established a new benchmark in aircraft manufacturing, combining meticulous oversight with innovative techniques. to ensure the reliability and performance of each aircraft. This system was designed to address the complexities of large-scale wartime production, where high output had to be balanced with uncompromising standards of quality and safety. At the core of this system was a series of rigorous testing procedures implemented at multiple stages of production. Each component underwent thorough inspections to verify its compliance with design specifications before advancing to the assembly line. As the aircraft took shape, strategically placed quality checkpoints along the assembly process ensured that any defects or inconsistencies were identified and corrected promptly, preventing larger issues from affecting the final product. Once assembly was complete, each Warhawk underwent comprehensive performance validation, including ground tests and flight trials, to confirm its readiness for operational deployment. Feedback from field service teams further enhanced this system, allowing engineers to refine manufacturing processes based on real-world performance and maintenance data. The manufacturing team also devised innovative strategies to sustain production quality amid the intense pressures of wartime demand. The adoption of multi-shift schedules was a key advancement, enabling round-the-clock operations while preserving the rigorous oversight necessary for maintaining quality. This approach ensured a steady output of aircraft without compromising the reliability and performance that pilots depended on in combat. By integrating meticulous quality control measures with adaptive production strategies, the P-40's manufacturing process demonstrated a remarkable ability to meet the dual demands of quantity and excellence. This achievement not only solidified the Warhawk's reputation as a dependable and durable fighter, but also set a precedent for future advancements in aerospace manufacturing. Material conservation became a vital focus during the wartime production of the P-40 Warhawk, reflecting the broader need to maximize efficiency and minimize resource waste in a time of global scarcity. To address these challenges, the engineering team implemented a range of innovative strategies aimed at optimizing resource utilization without compromising the aircraft's performance or reliability. One of the key approaches was the strategic allocation of critical materials. Engineers carefully prioritized the use of high-performance alloys and components for areas of the aircraft subjected to the greatest stress or wear, while less critical parts were constructed using more readily available materials. This targeted approach ensured that essential components maintained durability and strength while conserving valuable resources. In addition to strategic allocation, waste reduction protocols were integrated throughout the manufacturing process. By refining production methods and closely monitoring material usage, the team minimized excess and recycled offcuts wherever possible. These efforts not only reduced costs but also improved overall efficiency. The standardization of components further contributed to material conservation. By designing interchangeable parts that could be used across multiple aircraft, the production process became more streamlined, requiring fewer unique materials and simplifying supply chain management. Additionally, alternative materials were explored and incorporated where feasible, substituting less scarce resources without compromising the Warhawk's operational capabilities. The P-40's design adaptation from the P-36 airframe proved instrumental in conserving development resources and accelerating production timelines. This approach enabled rapid entry into production and operational service, a crucial advantage during wartime manufacturing. The manufacturing facilities demonstrated remarkable adaptability, shifting from single-shift to three-shift schedules as worker training programs expanded. This transition markedly increased production capacity without compromising build quality. The government supported these efforts through the strategic placement of educational orders and the construction of new production facilities. The success of these manufacturing innovations became evident as the P-40 Warhawk fighter plane maintained consistent quality standards despite the unprecedented scale of production. The aircraft's robust construction and reliable performance in diverse combat conditions validated the effectiveness of these manufacturing breakthroughs. Weapons integration systems. The weapons integration system of the Curtiss P-40 Warhawk exemplified a remarkable balance between firepower and engineering precision. The evolution of its armament reflected continuous improvements based on combat experience and technological advancements. The P-40's armament configuration underwent significant changes throughout its development. Early models featured 2.50 caliber Browning and M2 machine guns mounted above the engine, synchronized to fire through the propeller arc. Similarly, the P-40 Warhawk retained these nose-mounted guns with an addition of 2.30 caliber machine guns in each wing. As combat experience accumulated, engineers shifted toward a more effective wing-mounted configuration. The P-40 Kitty Hawk marked a crucial advancement with 6.50 caliber machine guns mounted in the wings. This arrangement offered several advantages, such as improved accuracy through concentrated fire, enhanced maintenance accessibility, better weight distribution across the airframe, and elimination of synchronization gear requirements. The ammunition feed system incorporated innovative engineering solutions to ensure reliable operation under combat conditions. Each wing-mounted gun received ammunition through a belt feed mechanism, allowing for 150 to 200 rounds per gun capacity, synchronized ammunition feed rates, reliable operation in various flight attitudes, and quick ammunition replenishment capability. The engineering team designed the ammunition boxes to be mounted side by side in the wings, enabling efficient feed mechanisms for all 6 guns. As a result, the combined rate of fire provided substantial firepower against both air and ground targets. The weapons system proved exceptionally effective in combat scenarios. Nevertheless, its success depended heavily on the integration of several key components. The P-40's targeting capabilities excelled in certain combat situations, as evidenced by its performance in desert and jungle warfare. The engineering team focused on optimizing the convergence of gunfire, ensuring maximum effectiveness at typical combat ranges. The wing-mounted arrangement allowed for concentrated fire patterns, improved accuracy against moving targets, enhanced effectiveness in ground attack roles, and reliable performance in diverse weather conditions. Combat reports indicated that the P-40's armament package proved particularly effective against lightly armored targets. In desert operations, the concentrated firepower of 6.50 caliber machine guns demonstrated remarkable effectiveness against both aerial and ground targets. The weapons system's reliability became apparent in various combat theaters, where the P-40 established a reputation for rugged dependability. Sooner or later, this combination of reliable armament and robust engineering contributed to the aircraft's success in multiple roles, from air superiority missions to ground attack operations. Performance enhancement solutions. Engineering teams at Curtiss focused intensively on enhancing the P-40 Warhawk's performance capabilities through systematic modifications and improvements. Their efforts yielded significant results across multiple performance parameters. The P-40 Warhawk was a testament to engineering ingenuity, achieving an impressive maximum speed of 362 mph. This performance was a result of meticulous attention to aerodynamic refinement and drag reduction, ensuring the aircraft remained competitive across various operational altitudes. For instance, the Warhawk could reach speeds of 306 mph at 5,000 feet, accelerating to 344 mph at 15,000 feet, with slightly diminished velocities of 342.5 mph at 20,000 feet and 326 mph at 25,000 feet. These figures reflect the careful balance between power and efficiency maintained by the engineering team. Each variant of the P-40 underwent iterative enhancements to refine its speed and overall performance. Engineers paid particular attention to reducing drag and improving the aircraft's aerodynamic profile, achieving substantial results in the P-40N variant. This version incorporated lightweight structural components, significantly reducing the overall weight of the aircraft. It also featured smaller diameter undercarriage wheels, which minimized aerodynamic resistance, and advanced aluminum radiators and oil coolers, which improved cooling efficiency while contributing to weight savings. These innovations collectively allowed the P-40N to excel in speed and agility, making it a formidable asset in diverse combat scenarios. The Curtiss P-40 Warhawk stood out for its exceptional maneuverability, particularly at medium and high speeds. Among early monoplane designs, it was renowned for being one of the tightest-turning aircraft in its class, a quality that gave it a distinct advantage in aerial engagements. Whether battling over the deserts of North Africa or the icy expanse of the Russian front, The P-40's turning capabilities often tip the scales in favor of its pilots, allowing them to outmaneuver opponents and maintain superiority in dogfights. This impressive maneuverability was the result of deliberate engineering advancements aimed at enhancing the aircraft's agility. The design incorporated a structurally robust airframe capable of withstanding the stresses of high G-turns without compromising integrity. Careful attention to weight distribution ensured the aircraft remained balanced and responsive during rapid maneuvers. Additionally, the control surfaces were refined to provide precise handling, allowing pilots to execute tight turns with confidence. The engineers also optimized the aircraft's aerodynamic profile, minimizing drag while maintaining lift, which further contributed to its agility. Collectively, these innovations made the P-40 a versatile and formidable fighter across multiple theaters of war. Straight away, engineers recognized the P-40's primary limitation, its effective altitude ceiling of approximately 12,000 feet. To address this challenge, they developed several engineering solutions. The P-40F variant incorporated the Packard 1.6 501 Merlin engine with a 2-speed supercharger, which undeniably improved high-altitude performance. This modification resulted in better performance at altitudes above 30,000 feet. The XP-40Q represented the pinnacle of altitude performance engineering for the Warhawk series. This variant achieved maximum speed of 422 mph at 20,500 feet, climb rate of 4,410 feet per minute at 5,000 feet, service ceiling of 39,000 feet. Formerly restricted by its single-stage, single-speed supercharger, the P-40's performance at high altitudes improved through continuous engineering refinements. The aircraft maintained good high-speed handling characteristics, enabling it to effectively engage enemy aircraft across various altitude ranges. The engineering team's focus on performance enhancement yielded an aircraft that, explicitly in low to medium altitudes, proved highly effective in combat operations. The P-40 consistently demonstrated superior dive speeds compared to contemporary fighters of the early war period, making it a formidable opponent in vertical maneuvers. Maintenance engineering. The maintenance engineering of the Curtiss P-40 Warhawk represented a significant advancement in military aircraft serviceability. The semi-modular design approach enabled efficient maintenance operations across diverse combat environments. The P-40 Warhawk's design prioritized maintenance accessibility through strategic component placement. The aircraft's structure incorporated numerous access panels, enabling technicians to reach critical systems without extensive disassembly. The engineering team developed a comprehensive maintenance system that included quick-access engine cowling panels, strategically placed inspection ports, tool-free access to routine service points, and modular component architecture. The P-40's repair-oriented design philosophy became apparent through its structural configuration. The engineering team implemented several innovative features that facilitated swift repairs in field conditions. A notable example was the specialized truck rig system at the Buffalo plant, which demonstrated the aircraft's modular nature even during assembly. The P-40 Warhawk was designed with a strong emphasis on ease of repair and maintenance, a philosophy that proved invaluable in wartime conditions where field repairs were often necessary. This design ethos was evident in the aircraft's structural configuration, which prioritized modularity and accessibility. Engineers at the Buffalo plant highlighted this modular approach with the use of a specialized truck rig system during assembly. This system not only streamlined production, but also showcased the P-40's straightforward design, which allowed for rapid disassembly and reassembly, a critical advantage for operational readiness in the field. The aircraft's repair-oriented design was further supported by an exceptional maintenance documentation system. Curtiss engineers developed a comprehensive set of technical manuals, each tailored to specific aspects of the aircraft's upkeep. These manuals were updated regularly to ensure accuracy and relevance, reflecting the evolving needs of maintenance crews. The Erection and Maintenance Manual provided detailed assembly guidelines and was updated quarterly, ensuring mechanics had up-to-date information for putting the aircraft into operational service. The Structural Repair Manual, updated semi-annually, offered precise instructions for assessing and addressing damage to the airframe, enabling swift restoration of combat readiness. Monthly updates to the service instructions manual ensured crews had clear guidance on routine maintenance tasks to keep the aircraft performing at its peak. Lastly, the parts catalog, updated biannually, served as an essential reference for locating and replacing components, further simplifying the repair process. Together, these innovations made the P-40 one of the most maintenance-friendly aircraft of its time, allowing it to remain a reliable asset even in the most challenging wartime environments. The P-40 Warhawk's standardized components across its various models represented a significant leap forward in the realm of aircraft maintenance engineering. By embracing an interchangeable parts system, Curtiss engineers effectively minimized the logistical complexities associated with maintaining a fleet of combat aircraft. This innovation not only reduced the volume of spare parts that needed to be stored but also streamlined repair processes, ensuring that damaged aircraft could be returned to service more quickly. This standardization was applied to critical components throughout the aircraft. Control surface elements, such as rudders, ailerons, and elevators, were designed to be interchangeable across multiple variants, enabling rapid replacements without the need for extensive modifications. Similarly, engine accessories, including carburetors, fuel pumps, and ignition systems, were standardized to ensure compatibility and ease of maintenance, regardless of the specific variant in use. Landing gear assemblies, a vital aspect of operational reliability, were also designed for cross-variant compatibility, simplifying repairs and reducing downtime. Furthermore, hydraulic system elements, such as actuators and reservoirs, followed the same philosophy, ensuring that mechanics could address issues swiftly and efficiently, even under the challenging conditions of wartime operations. The engineering team's focus on standardization yielded remarkable results in field operations. The P-40 demonstrated exceptional serviceability rates, even when operating from rough frontline airstrips. The aircraft's robust construction, combined with its maintainable design, enabled rapid turnaround times between missions. The maintenance system's effectiveness became evident throughout the aircraft's operational history. Technical crews could perform routine maintenance tasks with minimal specialized equipment, a crucial advantage in forward combat areas. The P-40's design allowed for field repairs using standard tools and equipment, reducing the logistical burden on maintenance units. The documentation system supported these maintenance capabilities through comprehensive technical manuals. These publications covered everything from basic servicing to complex structural repairs. The engineering team regularly updated these materials based on field experience and combat feedback, ensuring maintenance procedures evolved with operational requirements. The P-40's maintenance engineering also incorporated innovative solutions for specific combat-related challenges. For instance, the cooling system design allowed for quick inspection and servicing, while the armament installation facilitated rapid ammunition replenishment and gun maintenance. The standardization efforts extended beyond individual aircraft components to include maintenance procedures themselves. This systematic approach enabled maintenance crews to develop consistent routines, reducing service times and improving reliability. The engineering team's attention to maintenance requirements influenced subsequent aircraft designs, establishing new standards for military aircraft serviceability. Evolution through variants. The Curtiss P-40 Warhawk's evolution through multiple variants exemplified continuous engineering refinement based on combat experience and technological advancements. From its inception, as part of Curtiss's Hawk line of fighters, the P-40 underwent substantial modifications that progressively enhanced its combat effectiveness. The development of the P-40 Warhawk fighter plane marked a pivotal moment in military aviation history, beginning with a bold adaptation of the Allison V1710 liquid-cooled inline engine to the P-36 airframe. This innovative modification significantly reduced aerodynamic drag, resulting in a dramatic improvement in the overall performance of the aircraft. This transformation laid the foundation for a series of systematic advancements that defined the P-40's evolution across various models, each tailored to address specific operational demands and enhance combat effectiveness. The early P-40 billion variant introduced critical defensive features, including pilot armor and a bulletproof windscreen, which provided increased survivability during engagements. The P-40C followed with self-sealing fuel tanks, a vital improvement that reduced the risk of catastrophic fuel fires in battle. The P-40 brought a redesigned nose and an improved radiator, which optimized the aircraft's cooling system and streamlined its profile for better aerodynamic efficiency. With the P-40A, engineers focused on firepower, enhancing the armament configuration to increase its lethality against both aerial and ground targets. The culmination of these innovations was the P-40N, which became the most widely produced variant, with over 5,000 units manufactured. This version represented the pinnacle of the Warhawk's engineering evolution, incorporating several major advancements. A redesigned canopy provided improved visibility, giving pilots a crucial edge in situational awareness during combat. Lightweight structural modifications further enhanced the aircraft's agility and overall flight performance, making it more maneuverable in dogfights. The P-40N also featured an increased external load capacity of up to 2,500 pounds, enabling it to carry more bombs or auxiliary fuel tanks. These changes extended its operational range significantly, with a ferry range of up to 3,100 miles, making it suitable for long-distance missions and improving its versatility across various theaters of war. The engineering team's focus on weight reduction proved particularly successful in the P-40L variant, where they removed approximately 450 pounds of weight. This modification fundamentally improved the aircraft's performance characteristics without compromising its combat effectiveness. The evolution of the Curtiss Warhawk's design was heavily influenced by combat experience, with battlefield feedback driving continuous improvements to meet the demands of modern aerial warfare. The initial P-40 variant, while innovative for its time, was equipped with relatively modest Armament 2 machine guns mounted on the nose. As pilots encountered increasingly challenging combat scenarios, it became evident that enhanced firepower and adaptability were essential for the Warhawk to remain competitive. Early modifications addressed these needs by introducing wing-mounted .30 caliber machine guns, significantly increasing the aircraft's ability to deliver sustained firepower during engagements. Additionally, hardpoints were added under the wings to carry bombs and rockets, allowing the P-40 to serve effectively in ground attack roles. These enhancements transformed the Warhawk from a pure fighter into a versatile multi-role aircraft capable of tackling a broader range of missions. As the Warhawk's role expanded, later variants saw even more substantial advancements. The P-40E model integrated 6.50 caliber machine guns, a configuration that provided unparalleled firepower for dogfights and strafing runs. This model became a benchmark for the P-40's combat effectiveness. The P-40F, equipped with the Packard Merlin engine, marked another leap forward, delivering improved performance at higher altitudes and area where earlier variants had struggled. The P-40,000 followed suit with the incorporation of the Allison V171073 engine, which enhanced overall power and reliability. The P-40N series represented the zenith of the Warhawk's development, with the N5 production block introducing a series of significant structural modifications. The spine after the cockpit was redesigned to improve the aircraft's aerodynamic profile, contributing to better overall performance. 2 aft windows were removed to simplify the structure and enhance durability. Additionally, angled decking was installed over the fuselage tank, optimizing the aircraft's weight distribution and reinforcing its structural integrity. These combat-driven improvements made the P-40 particularly effective in specific operational environments. Notably, many pilots in the China-Burma-India theater preferred the P-40N over both Mustangs and Thunderbolts, citing its superior reliability. The aircraft's effectiveness was demonstrated during Operation Ichi-Go in 1944, where P-40Ns and P-40Ms of the 14th Air Force successfully disrupted Japanese offensive operations. The engineering team's commitment to continuous improvement resulted in 31 variants by the end of World War II. This extensive development process yielded a total production of 16,802 P-40 aircraft, with 13,738 units serving in U.S. forces. The aircraft's evolution reflected a remarkable balance between combat requirements and engineering capabilities, primarily focusing on enhancing performance while maintaining the robust reliability that characterized the P-40 series. The Curtiss P-40 Warhawk stands as a symbol of wartime engineering ingenuity, excelling in durability, firepower, and adaptability across various combat roles. Its evolution through multiple variants highlighted continuous innovation, from improved weaponry to enhanced maintainability. With over 13,000 units produced, the P-40's legacy reflects a pivotal chapter in aviation history. What do you think was the most impressive feature of the P-40? Let us know in the comments, and if you enjoyed this video, please comment one. Thank you for watching.